Okay, now we're going to talk about molecular term symbols in this lecture, which is really just describing the organization of electrons in a molecule. We've talked about atomic term symbols before, and those are much simpler because in an atom, there are no rotations and vibrations, there's only electronic states, and the organization of electrons is really all we care about. There's not really nuclear motion that we have to think about. Now, molecular term symbols are more complicated because now the orbitals are not atomic orbitals, but they're molecular orbitals that are built from combinations of atomic orbitals. And so molecular orbitals have funnier shapes where angular momentum might not be a totally good quantum number like it is in atoms. And in the case, in atoms, our atomic symbol or our atomic term symbol notation looked like this: 2s plus 1, where s was the number of unpaired electrons, capital L, which is the angular momentum, and J, which is the total angular momentum. So this is the angular momentum from the orbital L. This is the spin-orbit coupling, total angular momentum J, and S is the spin. Now, molecular term symbols are going to be important because just like in atoms, we want to identify and communicate to other scientists where the electrons are organized in the molecule, just like we're communicating that in terms of an atomic term symbol. And for this lecture, we're really going to limit the discussion to diatomics. For polyatomics, you need to get into point groups, and that's better left to inorganic chemistry and other lectures. So let's talk something about molecular orbitals and those term symbols. In atomic term symbols, we really only had to consider unpaired, unfilled subshells, I should say. Right? So in atomic term symbols, we were mainly caring about, if all of these were filled, and that s orbital was filled, and this one was halfway filled, I really only had to think about these electrons to come up with this term symbol. Okay? And the case is going to be similar here, where we're only really going to be caring about these partially filled molecular orbitals. Okay, so in molecular term symbols, where the notation is like this, 2s plus 1. Now instead of L, it's lambda. I'm still only really going to consider, just like the atomic orbitals were partially filled molecular orbitals, right? And so if my molecular orbital picture looks like this, these are paired, maybe it's a triplet state like this, it's only these ones here I'm considering and assigning this. Okay, so where we came up with S was the spin of the electrons, how many were unpaired essentially, 1/2 for each unpaired electron. So 2 times 1/2 plus 1 would have been a 2, it's a doublet state, right? Same is going to be true for here. This S is also just the number of unpaired electrons. So if there are 2 unpaired electrons here, 1/2 from this, plus 1/2 for this other electron, S here is going to be 1, and 2 times 1 plus 1 would give us 3 here for the 2s plus 1, whereas this would have been 2 for the 2s plus 1. Okay, so that's pretty straightforward. The spin is still going to be the same in the molecular term symbol, right? What's going to be different here is L. And back here in L, we worried about these m sub L's and the p orbitals. These were the m sub L's plus 1, 0, minus 1. And we just said this L here in a shortcut was summing up all the m sub L's. Okay, so this would have been an m sub L of 1, which means my term symbol letter was P. Okay, that's all review from atomic term symbols. Here we're going to use the following rule. Here, a pi molecular orbital has an m sub L of plus or minus 1. And a sigma molecular orbital has an m sub L of 0. So back here when we were writing s or p or d orbitals, we knew it was 0, then it was +1, 0, -1. Then for d, it's +2, +1, 0, -1, -2. Okay, here we're simplifying everything in that these are all 0 for sigma, and for this pi molecular orbital here, it'd be +1 and -1. Okay, for degenerate pi molecular orbitals like this, just like if I had 3 electrons here, +1, +0, -1 would sum to 0, the same is true here. These would offset, right? And the summation of these two in terms of my m sub of L would be 0. Okay, so S follows the same rules. This L versus lambda, similar rules, just know that all these sigma orbitals are going to be zeros, and all the pi orbitals are going to be +1 and -1. Okay. Over here, our L equals 0 is capital S, our L equals 1 is capital P, our L equals 2 is capital D. Over here, L of 0 is going to be sigma, L equals 1 is going to be capital pi, L equals 2 is going to be delta, L equals 3 B. So S, P, D, F, kind of like we had over here. So some typical molecular term symbols would look like 3 sigma, or maybe 2 pi. Okay, what would this one be here as I've drawn it? Well, the m sub L's +1 and -1 sum to 0. So that means it's a sigma. The spin, there's 2 unpaired electrons, so S is equal to 1. 2s plus 1 is 3. So this would be a 3 sigma molecular term symbol for this organization. And remember, we're getting this organization off of our MO diagrams. Now, while J exists, it's somewhat sporadic. Some people use it, some don't. So we're not going to worry about some J term spin-orbit coupling analog in molecular term symbols. Okay? Instead, we're going to use some other notations. So 2s plus 1, lambda. And then there's gerade or ungerade, which we've talked about before, only here they're meaning something a little bit different. Okay, here we're talking about gerade and ungerade in a term symbol, not a single orbital. So we use this designation in really naming molecular orbitals, but now it's really about the wave functions combining for all the molecular orbitals we care about, and whether that is even, gerade in German, or uneven, ungerade, odd, in German. Okay, so whether all the electrons we care about making up the molecular orbitals that make up this combined wave function, whether that wave function has even character as a function like x squared, or whether it has odd character like x cubed, is what we're referring to in terms of gerade or ungerade. Remember, here we're communicating to other scientists what is our total wave function, what is our organization of electrons in the molecular orbitals. Now, the rule is going to be the following here. Gerade, if all partially filled molecular orbitals are gerade. So again, we have to go back to our molecular orbital diagram and see whether these are pi gerade or pi ungerade. These are sigma gerade or sigma ungerade. Okay, so it's gerade if all partially filled molecular orbitals are gerade. or if there's an even number of partially filled molecular orbitals that are ungerade. Okay, and you can think back to this idea of how functions multiply, right? If you have two odd functions, right, and you multiply, say, x cubed by x cubed, well, now you have a function that is even. And again, we're only really worrying about the partially filled ones here, just like we're worrying about the partially filled sublevels here, and not this so much when coming up with an atomic term symbol. We're doing the same thing here for molecular term symbols. So this is going to be gerade if all the partially filled molecular orbitals are gerade. So if the functions are x squared, x to the fourth, x squared, x to the sixth, it doesn't matter how many functions. If they're all gerade, they're always going to multiply together to make an even function overall. And the analogy here is molecular orbitals are these functions that we're multiplying together to get the total wave function that describes our system. Okay, so in that analogy, it makes sense that overall this thing's going to be gerade or even, an even function, if all of them are gerade, the partially filled molecular orbitals, or if there's an even number of partially filled molecular orbitals that are ungerade. Okay, it's going to be ungerade then if there's an odd number of partially filled molecular orbitals that are ungerade. Okay, so if there is, say, one of the molecular orbitals is ungerade, like x cubed, times a molecular orbital that is gerade, x squared, well, then we get x to the fifth, still ungerade. So again, we're worrying about our molecular orbital diagrams. Maybe they look like this. Some of these are filled. Maybe I stop here. Then I just consider this one, right? In this partially filled molecular orbital, if this is a pi ungerade molecular orbital, right? There's one partially filled molecular orbital, an odd number of ungerades, so this would be an ungerade configuration, okay? Whereas this would be a gerade configuration, because there's an even number, 2, of ungerade molecular orbitals. Okay, so that's how we come up with evengerade, gerade, or ungerade. The last thing you'll see, okay, is plus or minus. You'll sometimes see this, but only for sigma terms. So if the angular momentum here is 0 and it's a sigma term, then I have to worry about plus and minus. So I don't use plus or minus on pi, I only use plus or minus on sigma molecular term symbols. Sigma minus versus sigma plus. This means the whole molecular wave function here remains the same upon reflection through the plane of the internuclear axis. Now remember, these are all just diatomics we're dealing with. So there's only one internuclear axis. That's how you define sort of the axis you care about. And so for diatomics, that's always going to be this singular plane. We're not going to worry about orienting this thing at some weird angle and worrying about the plane like that. It's always just this internuclear axis. Okay, so sigma plus for an orbital, or a combination of orbitals, I should say, that remains the same upon reflection through the plane of internuclear. And sigma minus, well, you can guess, is when this changes sign upon reflection. Now, this is not obvious based on this definition, because again, this is not the wave function of a single molecular orbital. This is the wave function that is a combination of all the molecular orbitals multiplied together. Okay, it's hard to visualize. It's not a single molecular orbital always, but could contain multiple molecular orbitals. So here's the simpler rule for plus versus minus. Plus, when all molecular orbitals are filled, or all partially filled molecular orbitals are sigma. If some partially filled molecular orbitals have pi character, this is an if-then statement, then if it's a singlet state, that's going to be plus. Triplet state is going to be minus. Okay, so the shortcut here is that only triplet states here will have this minus sign on a sigma. Okay, so going back to this sort of example, where we had 3 sigma, right? We can identify this one actually as a 3 sigma minus. Why? Because these partially filled molecular orbitals that have pi character is a triplet, 2 unpaired electrons. Okay, it doesn't matter if it's a doublet, because if it's a doublet, it's not going to be sigma. It's going to be pi, and the plus minus doesn't apply. So let me repeat that because that's an often missed point. The plus and minus is only for terms that are sigma. That sigma is only possible here if both of these are occupied and offset. And that's why we only make the distinction, right, about triplet states or singlet states, because a doublet state would not be sigma, it would be pi. Okay, so that is sort of all the different types of naming here, whether it's gerade, ungerade, plus minus. Remember, plus minus only applies to sigma molecular term symbols. The 2s plus 1 is the same as it was in atoms. Okay, the L here, that's now lambda, the angular momentum, is still adding up m sub L's, but we number m sub L's 0 for all the sigmas, plus 1 minus 1 for the pi's. Okay, so let's look at a quick example here and consider the following. Okay, let's consider boron, the diatomic. The molecular orbital diagram you could write out, but I'm going to say here there's a 1 sigma gerade, 2 electrons in that. Then there's a 1 sigma ungerade, antibonding, 2 electrons in that. Then there's another set, so these are the essentially 1s electrons coming together. Then there's a 2 sigma gerade, 2 electrons in that, and a 2 sigma ungerade, antibonding, 2 electrons in that. Then there are the 1 pi ungerade molecular orbitals. There's 2 of them, and it's a triplet state, so there's 1 electron in each. Only these are partially filled, so those are the only things I care about when assigning the molecular term symbol. 2 unpaired here. So I know this is going to be a triplet. S is 1, 2s plus 1 is 3. Okay, pi molecular orbitals here that are degenerate. 1 is plus 1, 1 is minus 1. This is the same analogy we've been using, or the same example we've been using. So my sigma of all the m sub l's here is 0. So it's clearly a sigma term. So I know this so far. Is it gerade or ungerade? Well, we can go back to our example here. And we have partially filled molecular orbitals, but there's an even number of partially filled ungerades, because there's 2 partially filled ungerades. So that makes it gerade overall. And then is it plus or minus? Well, some partially filled molecular orbitals have pi character, and it's a triplet state. Yes, this is a triplet state, so this should be minus. So the molecular term symbol here that describes the organization of electrons is 3 sigma g minus. Now, we're really just assigning here, the ground state organization. We're assuming here that Hund's rules works, and they should here, right? Higher spin is preferred, right? Which is why this is going to be not 2 electrons in a single one of these molecular orbitals, but them split up to maximize spin multiplicity. That's Hund's rule. That will be lower in energy. That's the ground state. Okay, so Hund's rules the first and Hund's rules the second, right? Where if it's the same spin multiplicity, you go with the largest angular momentum. In atomic term symbols, you do the same thing here. Hund's rule the third, we're not using a J term or spin orbit term, so we don't have to worry about that one. Okay. Another example we could think about is, well, what if all of the molecular orbitals are completely filled? Okay? If all of the molecular orbitals are filled, and there are no unfilled, so doesn't matter, maybe it's like this, and all these are filled. Okay, s equals 0, there's no unpaired, so 2s plus 1 is 1. Right? My m sub l's all offset, so my m sub l's are going to sum to 0. So this is clearly going to be a sigma. Right? We can go back and review. All partially filled molecular orbitals are gerade. Well, I guess we don't have it here, but it's going to be even when everything's paired up, so this should be gerade. Okay? And then plus or minus, plus if all molecular orbitals are filled. So this is plus. So this is going to be the term symbol always for completely filled molecular orbitals. And for atomic term symbols, we had the same thing. For completely filled atomic orbitals, it was always 1s0 was the atomic term symbol. So the same thing is going to be the case here. Only in molecular term symbols, it's going to look like this. Okay, so those are molecular term symbols. You can be asked to calculate it for a ground state or consider an excited state. For now, this lecture's really just been about diatomics. The reason you want to figure out term symbols, okay, is because you're going to see these things in the literature when you come across potential energy surfaces. Okay, and for something like oxygen, whose potential energy surface looks like this, where there's a Morse potential here that we've talked about, it's going to say something like X, 3 sigma G minus. That tells you, for oxygen here, how the molecular orbitals are organized. And of course, we've just done this term symbol. It's when you have this triplet state. Okay, but you're going to see some other diagrams on here, some other curves that look like this, and this might be labeled A1 delta gerade. Okay, and maybe another one here, like this, that is labeled B1 sigma gerade plus. And that's describing to you what's happening when you promote this electron to some excited state. Okay? So notice here, the way we write these term symbols come with a letter out front. X denotes the ground state. Capital A, first excited state. Of same multiplicity. Lowercase a, first excited state of different multiplicity. Okay, and now there's going to be some selection rules for what's possible here, right? We talked about the same thing with atoms, but now we're in molecules. So there's molecular term symbols and there's molecular selection rules. So the selection rules here for molecules are going to be similar to our atomic rule. Here, delta S equals 0. And delta L, or here delta lambda, the change in the angular momentum, must be 0 or plus or minus 1. Ungerade must change. And plus minus must not change. Okay, so these are the selection rules for molecular term symbols and what would be possible on a potential energy surface, so you know where to draw arrows and where you can't. Okay, and term symbols would denote transitions, like this would be a transition, this absorbing and getting promoted to. Let's make sure it's allowed here. So sigma is fine, triplet is fine. It has to become ungerade. And it must change to minus or plus. Well, this won't obey selection rules. So I guess you wouldn't have, oh, well, you can still have this transition, right? So imagine I wanted to think about this transition. The spin doesn't change, the lambda doesn't change, gerade to ungerade does change, but this would violate the plus minus staying the same. Okay, so this would be a forbidden type of transition. It might still be possible, but it would be forbidden in that case. Okay, so the selection rules, remember, are telling us what's most likely to happen, what's favored, not necessarily what will happen or won't happen, just what's much more likely. So this would be forbidden, and it'd be forbidden because the plus and minus changes. Okay? So again, you're going to have other, curves on this diagram. Maybe there's a curve up here that we'll call the B state. And the B state is this triplet sigma I've just talked about. And this is not allowed, it is forbidden. And so this does not really happen. Why should one care about that? Okay? The gap between these two, right, may or may not be a gap that oxygen sees very much. Right? So maybe a transition like this isn't allowed. And if it were allowed, then oxygen would be absorbing that light, and maybe the color of our atmosphere would not be clear, right? Because it would be absorbing some partial light from the sun. And so whether or not these transitions are allowed or forbidden really dictate a lot of properties of the molecule we see in the real world, and tells us, ozone may have a favorable transition here, while oxygen doesn't. And so maybe ozone absorbs a lot of UV radiation and protects us from that harmful radiation from the sun. So you'll see diagrams like this. You'll see arrows drawn. It's only going to be drawn to states usually with satisfying these selection rules. And that dictates something about the photochemistry that is allowed in that molecule. So that'll do it today for molecular term symbols and some spectroscopy in terms of the allowed and forbidden transitions between these different term symbols. Up next time, we'll get into vibrational spectroscopy and then rotational spectroscopy to follow up on that. That'll do it for this lecture. See you next time.